Welcome back to HackCode. In this video, we're tackling an essential problem for coding interviews, jump game from LeetCode. This problem is great for learning recursion, memoization, and greedy algorithms. We'll explore three approaches: a simple recursive solution, an optimized memoized version, and a highly efficient greedy approach. Let's break down the problem step by step and understand how these solutions work. So sit back, relax, and let's dive in. So, what is the problem statement? You're given an integer array nums. You were initially positioned at array's first index, and each element in the array represents your maximum jump length at that position. Return true if we can reach the last index, or false otherwise. So let me just explain you with an example. Let's consider the example 1. So in example 1, we have nums is given as 2, 3, 1, 1, 4. I represent this using 2, 3, 1, 1, 4 here, and this guy would be there at the index 0 initially. So these are the indices we have. So here each element in this particular index represents the maximum jump this guy can take. Okay, so that means that if he has a 2, then he can make 1 jump or 2 jumps. If he has 3, then he can make 1 jump, 2 jump, or 3 jumps. So basically this is the cap of the jump he can do, and minimum is 1. And it's not the case where like if he has 0 he can make 1 jump, but what I meant is this is a maximum jump. Okay, so that means here he can take lesser number of jumps as well. So he can choose to make 0 jumps, or he can choose 1 jump, 2 jump, or 3 jumps. That's the idea, guys. But we don't take 0 jumps because we have to jump. Okay, but if the array has element 0, then we have to take 0 jump, right? Like we don't have any other option. He should stop there and we can't jump further. That's the idea here. Okay, so here in example 1, so let's consider the path 1. Okay, so firstly, let me just consider 2 jumps here. So he can take 2 jumps. Okay, from here, maximum jump possible is 1. So 1 jump, from here 1 jump. So he reached the end, so we can return true. And there is another possible path as well. So he can take 1 jump here, and then from 3, he can take 3 jumps, and he reached the end. So this is another path possible. There are also other paths possible. Okay, so from 3, he can take only 1 jump. Okay, from here 1 jump, from here 1 jump. So likewise, there are paths possible. Okay, it's not that single path. So we don't care about which path he takes. We care about if he reached the end or not. That's the idea, guys. So in example 1, we turn true because he can reach the end. Okay, so in example 2, we have nums is given as 3, 2, 1, 0, 4. So here what is the case? So if you take 3 jumps here, he reaches 0. Okay, from 0 he can't go further, so this path is not valid. So from 3, if he take 1 jump, then he reaches 2. So from 2, if he takes 2 jumps, he reaches 0. Then from 0, he can't jump further. So it's not possible. So let's consider the case where from 2, he makes 1 jump. So even if he makes 1 jump, he lands at 1. Then from 1, he can make only 1 jump. So there is no other path which is leading him to the end, right? So he can't reach the last index. So we have to return false. Okay. So let's look into the constraints here. So first constraint is nums length is an inclusive range of 1 to 10 power 4. So in the best case, nums length is 1, and the worst case, it is 10 power 4. What should we learn from this? So first thing is we can perform 10 power 8 operations per second. So more than that, it would be time limit exceeded. So upper limit of n is what? 10 power 4 here. So if 10 power 4, then if you do n square, it is 10 power 8. Okay. So if our solution complexity exceeds n square, then it won't be accepted. So our solution complexity should be less than or equal to O of n square. So that's the idea, guys. This is what we should look from this constraint. Second constraint is nums of I is in the inclusive range of 0 to 10 power 5. So basically here we have this jump range, right? That would be in the inclusive range of 0 to 10 power 5. So he can take either 0 jumps or 10 power 5 jumps. Okay, this is the boilerplate code given. We have a can jump method. This takes nums, which is list of integer, and returns the boolean. This boolean indicates if we can reach the last index. So now let's look into approaches. Before we get started, I want to remind you about our exclusive blind spot info post. This carefully curated collection covers essential coding interview problems to help you master the most common patterns and excel in your interviews. Whether you're prepping for FANG level interviews or just sharpening your problem-solving skills, these problems will ensure you're ready for anything. Even if the exact questions aren't asked, they cover all the important patterns. So be sure to check out our playlist and stay ahead of the competition. So let's look into the brute force approach. This is based on recursion. So what is the intuition here? So we recursively check if each index can reach the end by making all possible jumps from each position. So basically here the intuition is from each position we make all possible jumps. That means that if we have a position of value 2, we try making 1 jump and we try making 2 jumps, and we see if any of these paths could lead to solution. So if any of these paths could lead to a solution, then we can return true. That's the idea. So although this is a straightforward, it has significant redundant subproblems, making it inefficient. So don't worry about this subproblem part. I'll just show you in a recursion stack deeply in later point of the video. So let's look into algorithm. In step 1, if index is the last index, then return true. This is the base case for success. So for our recursion functions, we should have the base case, right? Else the function would keep on calling itself and it would give us the recursion depth exceeded error. So for that cases, we should have the base case to stop the recursion at one point, okay? So here we checking if the index is the last index, then it means that we traversed to the last index and which is our goal. So in that case, we can return true, right? So that's why we can return true here. In step 2, if index is beyond the array bounds or leads to 0, return false. This is the base case for failure. What does this mean, index beyond the array bounds? It means that we got the index such that like out of the array bounds. Like if it is a greater than or equal to array length, that means that it is not a valid index. The valid index is only from 0 to array length minus 1, right? So for index exceeding the array length cases, then we can just return 0. And also in cases where we have the jump value as 0. So for jump value as 0, we can't make it further, right? That's why we had to return false. So here, so this is the second example case wherein from this position we can't go further, so we had to return false. So in step 3, calculate the furthest reach from the current index as reach is equals to index plus nums of index. So this is just a mathematical representation of calculating the reach. So let's say you're in index 0, then what is the maximum reach possible from this index? So this is just like from 0 plus 2, right? From here we can reach here. So here the formula is what? Index plus this value. So that's the idea, guys. We're just adding these two values, that's all, okay? So that's why we do reach is equals to index plus nums of index, okay? In step 4, for each position from index plus 1 to reach, call helper of I recursively. If any recursive call returns true, return true for the current position. So you got the idea, right? So we discussed before that for each index we just try all possible cases. So if we have a 2 value, then we can explore from 1 to 2 values, right? So if you have value 3, we can try jumping 1 position, 2 position, and 3 positions. So basically from index plus 1 till the reach value, we can try all possible paths, right? So this is that step, okay? And we return true if any of the recursive call returns true. So basically if any of the call returns true, that means that we were able to reach the end, right? So that's why we return true. So step 4 is just opposite of it. So if no path works, we return false. So basically if no path leads to the end of the array, then we should return false. So now let's look into the code. So this is very simple. So firstly we define the recursive function as we just discussed. This is the base cases we have. So in step 1 we're just checking if index is equals to length of nums minus 1. That means that we reach the last index, so we have to return true. In step 2, this is also a base case where out of bound check or no jump potential check. So here this is the out of bound check. So basically if index is greater than or equal to length of nums, that means that we have crossed our valid indexes, so we have to return false. And also we have the other case where if nums of index is equal to 0, that means that this case, okay, so in that case we can't go further, that's why we return false. So that's why we have the OR condition here. If any of these two conditions satisfy, we return false, okay, because we can't make it to the end of the array. So next is we calculate the maximum reach. So we just discussed the formula for maximum reach, right? So this is like reach is equals to index plus nums of index, okay, this formula. So next is to try all reachable positions. So we are checking the range of index plus 1 and reach plus 1. Why reach plus 1 here? Basically we can go till reach, but this is exclusive in the range function. That's why we specify reach plus 1, and which would form the range from index plus 1 to reach including, okay. So that's why we pass plus 1 here, and in this range we check if helper of I returns true. In that case we return true. So basically here if helper of I means it is checking that if this is true. If this is true, that means that we can reach the end of the array, so we can return true here. So in other case where if no path leads to success, we have to return false. So that's why here we are returning false, okay. So basically if we could reach the end of the array, this would have been returned here. Else after trying all reachable positions, we can return false, okay. And here we are calling helper of 0. So basically here we shorted the first index, right? So that's why we call helper of 0. So here we are returning helper of 0. This helper of 0 in turn return the boolean, which is true or false, okay. So what are the complexities here? The time complexity is O of 2 power n. As we explore all possible paths, doubling the number of possibilities at each step, leading to an exponential time complexity. So basically at each path, we are exploring all possible positions, right? So it is exponential time complexity. And the space complexity is O of n due to the recursive call stack. So basically the maximum length of the recursive call stack is n. So this is what length of the given array nums. So that's why the space complexity is O of n. I got the code ready here. Let me try running this. So the HackCode solution with the two cases. Let me try summoning this. So we see that the time limit is exceeded and only 74 out of 173 test cases surpassed. This is because our solution is having the exponential time complexity and it won't be scalable for the larger arrays. So that's why we need to optimize our solution. So let's look into the optimized approaches. So let's look into recursion stack. So I considered the example nums is equals to 2, 3, 1, 1, 4, and here this is the indices. So we are calling our recursive function, which is helper of index. In helper of index, we have the two main steps, that is calculating the reach and exploring the reachable positions. So here we're starting with index 0. So from index 0, we have two possible jumps, right? So from index 0, what we have the value as 2. So here we can explore one jump or two jumps. So that's why we pass helper of 1 and helper of 2. So at index 1, we have the value 3. That means we can explore three possible jumps. That is going to second index, going to third index, going to fourth index. So that's why we call helper of 2, 3 and 4. Okay. So that's how we have the calls going on recursively here. So similarly from index 2, we have only one possible path, which is going to index 3. That's why we call helper of 3. So from helper of 3 also, we have only one possible path, which is going to fourth index. That's why we call helper of 4. And from helper of 4, we can just return true because this is the base case we have, right? And this is a lost index. So that's why this returns true. And similarly, we have all these cases. So if we observe this closely, we are calling the same subproblem again and again. So here the helper of 2 is called for twice, and helper of 3 is called for thrice, and helper of 4 is called for 4 times. So here, if this is nothing but redundancy, right? So here we are calculating the same subproblem again and again. That is what showing our solution. Okay. So here, instead of computing our subproblems again and again, what if we store this results once and reuse next time? So that's the idea of dynamic programming, guys. So basically, we compute the subproblem once and then we reuse it for the solving the bigger subproblem. Okay. So in that case, you'll be computing this helper of 2, 3, 4 only once and storing it in the cache. So next time we call this helper of 2 or 3 or 4, we'll be taking the value from the cache instead of computing it again. So that's the idea, guys. So let's look into approach 2, which is recursion with memoization. This is nothing but the top-down dynamic programming approach. So what is the intuition here? This approach optimizes the recursive solution by using a hash map to store already computed results, avoiding redundant calculations for overlapping subproblems. So basically here, we use the hash map to store the already computed results. And next time, if we get the same call, we just return from the hash map instead of computing it again. So that's the optimization we're doing here. So let's look into algorithm. Step 1, if index is the lost index, we return true. This is same as the previous approach. And in step 2, if index is beyond bounds or has 0, we return false. This is also same as the previous approach. Step 3 is what the difference here. If index is in the hash map, return the cached result. So here we using the index as a key in the hash map, okay, and we storing the value computed for that particular call. So if index is there in the hash map, that means that we already computed this subproblem, so we return from the hash map instead of computing again. Okay, so this is the optimization. In step 4, calculate the reach and recursively check all positions from index plus 1 to reach. This is also same as previous approach. In step 5, we cache the result in the hash map before returning. So here this is something different from the previous approach, wherein we just cache the result before we return. Okay, so let's look into the code. So as compared to previous approach, we have some minor code changes here. So, but later point of the video, I'll show you how to change this recursive function to a memoized version with just a one line change. Okay. Firstly, we defined our memo, which is a dictionary or hash map here. This is used to store the results. So first two steps are same in this function as previous approach. In step 3, we return the cached result. Okay. We're just checking if index in memo and then we return from the memo. Okay. So we just returning memo of index. So in step 4, we check all reachable positions as previous approach. But here before returning, we just store the result. So here also we're doing the same and returning it. So that's the difference. Okay. Now let's look into complexities. The time complexity is O of n square because we explore up to n positions for each index. Okay. And we compute the each index only once. So that's why it is O of n square. Okay. Space complexity is O of n. This is for the recursion stack and the memo dictionary. So the recursion stack would be of length what n. And memo dictionary would also be of length what n. So it is actually O of 2n. But this 2 is an ignorable factor. So that's why it is O of n. Okay. So now let's look into how to change this recursive function to memoized version with just one line of change. We just need to add at of cache, then it would be becoming the memoized version. Let me try submitting this. So we see that all test cases are passed. Okay. So with just one line of change, we can convert this into the memoized version. So how is this working? This basically is same as a hash map concept, but we are using the decorator here. So this decorator stores the computed results for the particular parameters of the function. So if you get a call to the function again with the same parameters, then it would be looking into the cache and returning the values instead of computing it. Okay. So this is the same concept, but with just a decorator. Okay. So now I got the code ready for the memoized version with hash map. Let me try running this. This accepts solution with the two cases. Let me try submitting this. So this also accepts solution for all the test cases we have. Let's look into further optimizations. So let's look into our greedy approach. This is the most optimized approach we have, and here the time complexity is reduced to often, which is a linear time complexity. So what is the intuition here? The greedy approach leverages the simple observation. While traversing each position, keep track of the furthest index you can reach at any point. This allows us to decide whether reaching the end is possible in a single pass. Simple, right? So basically here for each index, we keep track of the maximum reachable index. Okay, so if we are at the index 0, then what is the maximum reachable index? It is 2, right? So 0 plus 2, which is 2. So if we are at 3, what is the maximum possible index here? 1 plus 3, which is 4. So here only with the 2 jumps we can make it to n. So basically we keep track of the furthest possible index, and then we jump only if we have the furthest possible index possible. So that means here consider we have 2, and then we thought of having 2 jumps, but again on the way to 2 jumps we saw 3. That means we can ditch 2 and then we can jump 3 times. So that's how we can reach more early, right? After 3 as well we are not satisfied, so we just explore if there is a maximum possible afterwards. So we go here like 3 jumps, but while on the way we check if there is any further possible. So the core idea is we keep track of the maximum possible jump, and when we encounter the more maximum possible jump, we just switch to that one. So basically we will reach the old maximum possible jump and go to a new maximum possible jump. That's the idea, guys. The main idea is we have to consider the local optimal solution, and that would lead to the global optimal solution. This is what the greedy approach. Okay, so let's look into algorithm. Firstly, in step 1, we initialize the max reach to keep track of the furthest reachable index. Okay, in step 2, loop through each index. If current index exceeds the max reach, return false. So that means that we can't reach the end of the array if current index exceeds the max reach. That's typically in the case where we encounter 0 in our way. Here in this case, when we reach the index 4, our maximum reach would be only till what? 3. So here index is greater than the max reach. So in this case, we have to return false, right? So this is that case only. In step 3, update the max reach based on the jump potential at the current index. So this is something we discussed, right? So basically the max reach would be changing based on the current jump position. Okay. In step 4, after the loop, return true if the end is reachable. Okay, so basically here if we are able to complete the loop, that means that we are able to reach the end of the array. So we return true here. Okay, so let's look into the code. So in step 1, we just initializing our max reach to keep track of the furthest reachable index. Next is we just iterate over this each index and update the max reach. Okay, so that's why we're using the for loop here. It would form the range from 0 to length of nums minus 1. Okay, so because this is the exclusion range, right? That's why I will get till length of nums minus 1. So if current index is beyond the max reach, we have to return false, right? We just discussed in step 2. So that's why here if I is greater than the max reach, we can return false. This is that example 2 case we discussed. In step 3, we update the max reach based on the current potential jump. So basically max reach is the maximum of the current max reach and I plus nums of I. So I plus nums of I is what the current jump potential, and the max reach is what the previously stored max reach. Okay, so basically we want the maximum value to be picked at each position. So we just discussed here, right? So while we move from 2 to 3, we can ditch the 2. So we can ditch the max reach from 2 and then update the max reach to 3, and then we proceed with 3 jumps. Okay, while proceeding with 3 jumps also, we are not satisfied. We still can ditch 3 if we get a more maximum value. That's the idea. So at the end, we return true, because if we can't reach the end, that would be decided here within the for loop. So that's why when we exit the for loop, it means that we are able to traverse till end of the array. So that's why we have to return the true here. So let's look into complexities. The time complexity is O of n, as we iterate to the array only once. And space complexity is O of n, as it requires a constant space, because here we just using only one variable max reach, and this variable is always constant and it is not dependent on the input array size. So it is constant space. That's why the space complexity is O of 1. So I got the code ready here. Let me try running this. So this is accept solution for these 2 cases. Let me try submitting this. So this accept solution with all the test cases and beats almost 44% of users. Cool, right? And that's your wrap on solving the jump game using 3 different approaches. If you found this breakdown useful, drop a comment below and share your thoughts. Don't forget to like the video, spread the word to your fellow coders, and hit the subscribe button for more in-depth coding tutorials. Also, do follow on Instagram for the latest updates. And if you're looking for resources or have some doubts and want to discuss, join our Telegram community. See you in the next one.